Okay, it's been over 3 weeks since that last video. During that time, I had to do a lot of head scratching, a lot of searching, research, chat GPT, all kinds of things. And I found out that the memory blow up was not so much the computer inadequacy, but it was the problem with the code. And the code now uses Estimator, and the estimator is called AER estimator, which is specifically designed for the AER, which is the way of doing quantum computing, but you're using a classical computer for two reasons. One, you want to check it out before you run it on there, or because you're poor and you can't afford to actually link in there and spend a bunch of money having the quantum computer actually do it for you. I'm going to look at the code a little bit this time, and with you, hopefully, if you're still with me on this video, we can understand what's happening. So first, let me get rid of my image, which for some reason is awfully dark today. I'm not sure why, but take a look out here. These are my files, and I'm going to close up one of these things called project, and you'll see what the different structure is. And here's some of those that failed. They failed not on the real basic or elementary bases, which are good for teaching, but when you actually want to get proper geometries of the ammonia molecule, you need higher bases, and this made these particular ones blow up. And as I said earlier, the estimator used was the same estimator that would be used on an actual quantum backend rather than this AER. Let's look at my project here, and you'll see that it spreads out into multiple files. Okay, here's all these different Python files rather than just one. And the main program that runs this, let's go down to main, and there, that's all that main runs. It runs this thing called a run basis sweep method, and it includes the bases of STO 3G, 32161. Okay, anyway, these are the higher bases. Not my job to explain the different bases here, but I'll obviously have to do that job at some point. Let's find out where run basis sweep is identified. Run basis sweep is in scaling runner. There's run basis sweep. That also looks very small. Notice here's the bases, that list of the strings of those different things, and the mode is AER. It could be IBM because I have connected to the IBM backend, but it's just this AER version of the code. Okay, or that's actually the backend that I'm running it on. And in these bases, I run experiment. Okay, and then I append the results from each experiment that's run in this for loop for all the different bases. Let's find out. Here's run experiment. Let's see, here's the method run experiment, and it does build NH3 molecule and build qubit Hamiltonian. And let's see, what have we got here? Build Hamiltonian. Let's see, find out the NH3 molecule is in this thing, the Python self-consistent field. And let's see what's going on there in this one. All right, here's build NH3 molecule, which this thing isn't nearly as hard as we thought. Here's one of the bases here that's shown, and there's the geometry of the molecule. These quantities here look like they're just commented out with the 3 quotes. Maybe it figures that out. Not sure what associates it with the NH3 molecule, but later on we can work with more complicated molecules. Notice I'm kind of teaching myself as I go along, which is pretty much the way all these videos work. Now let's go back and find out where we do the Hamiltonian and see what the Hamiltonian method looks like. Well, that thing's a lot longer. Notice here, I think I see why those were commented out, because here we've got the NHH, and here's the geometries that we looked at over there. Let's see if that's still the same. Aha! The geometries are the same. So that's why those are commented out. Remember, I didn't really write these things. I kind of asked questions and I got some stuff back. So otherwise, I wouldn't be nearly as far as I am right now. Here was the NH3 molecule, the qubit Hamiltonian, then we printed a bunch of stuff out, memory profiler, and then we returned the results each time. And these results were appended to, and if you look down here, and here's all my results. So let's look at this and see if it starts to make sense. Here, the elementary one used 16 qubits, and as we progress up, the number of qubits starts to grow. The terms that are involved start to really get huge, down to here where we've got 509,000, and here's the runtime. This one runs 3 seconds, 30 seconds, all the way down to, let's see, that would be, it's okay, that's about 10 minutes there to run that. And notice the memory starts finally getting up to reasonable sizes. Here we're using 4 gigabytes of memory. So that's really a quick and very choppy explanation of how I got from something that was broken and took 13 terabytes to something manageable that only took 256 megabytes up to 4 gigabytes